Hello. So, we talk about Runge-Kutta methods for initial value problems. So, in the last lectures we have talked about Euler method, then modified Euler method. So, we introduced the concept of slope averaging, right. So, the generalization is, if you take an interval, you try to take some intermediate points and then take the weighted average of the slopes. This is a more generalization which leads to Runge-Kutta method. Okay. So, let us talk about the derivation is a little lengthy, because it is more technical based on the formula. You have to compare with the Taylor series expansion and then try to determine the coefficients and weights and all that. So, we have to be little patient while understanding the derivation. Okay. So, let us talk about this. So, as I mentioned, the concept is, within an interval, when you step from one x n, you know the data, and we try to compute the data at x n plus 1, right. So, that is what, because this is a single step method. So, we have been doing that. So, now what is the idea? Use several intermediate points A 3 h, so on, and then take the slopes at each point. So, that is weighted average, that is what I said. So, your approximate solution is y n plus h I 1 to L, the weights and slope at these intermediate points. Okay. So, as I mentioned, we are taking weights such that, and L points, L intermediate points, this L denotes L slopes, L denotes L slopes. Okay. And moreover, I started with A 2. So, in x n plus A 1 h equals to x n. So, that I have taken A 1 equals 0. This is just a convenience, so that there is a symmetry in the derivation, that is all, nothing serious about it. You can take even this is A 1, A 2, etcetera, there is no harm. Okay. So, now when you talk about star, so what is the first one? I starts from 1, therefore, x n is, so the first entry is y n of x n plus A 1 h. So, this is x n, this is okay. So, call this k 1. So, the next entry x n plus A 2, this is f of x n plus A 2 h y n of x n plus A 2 h, and we use a Euler. So, this is y n plus A 2 h y dash of x n. So, that means in Taylor series we have neglected the second order onwards, that is what we have. Okay. So, this is y n plus. So, this y dash f x n is f, right. So, this is A 2 h further, this can be generalized in the sense this is equals to f of A 2 h, this is k 1, right. So, I introduce k 1 there. So, this let us call k 2. Okay. So, see, please try to follow. We started here and f of x n plus a to h is this. Okay. So, then we used Euler, okay, for this is just Euler. Then this is nothing but k 1 as defined. So, now we have defined something called k 2. So, that means each slope at each point we are computing and we are giving a notation, right. So, now we move to the next, right. So, what is the next point? The next point is y n prime a 3. So, this is f of okay. So, still we have not used the concept of averaging. So, now the first time we are trying to introduce here, because where are we computing? We are computing y dash at x n plus a 3 h. So, there is already x n to x n plus a 2 h and from here to here. So, there are already two slopes involved prior to that, right. So, now we try to use the averaging concept. So, that is so this we have to, so this is y n plus the increment is a 3 h, then we have y dash of x n, right. So, this we try to get it in a weighted average sense. So, we introduce some notation b 3 1 y dash of x n plus b 3 2 y dash of x n plus a 2 h. See, this is at a 3 h. So, therefore, we have used past two slopes x n plus a 2 h. So, this is a weighted average. Okay. So, this can be simplified. This is a more generalization. So, we are not so much worried about the particular constants, because ultimately we end up with a generalization in terms of specified constants. Okay. So, this is plus. Okay. Now, I take h common here, this h, look at these constants, arbitrary constants. So, I try to, so this a 3 multiplied by b 3 1 divided by this. So, this we can call some new constant, and y dash of x n is just k 1 plus again a 3 multiplied by b 3 2 divided by this, this I call another constant, and y dash of x n plus a 2 h is k 2. Okay. So, it is a more technical, you should try to follow. Okay. First one, this is at x n, second slope is at x n plus a 2 h. So, that is k 2, then third slope is at x n plus a 3 h. Okay. So, this is our k 3. So, let me define k 1 is this, k 2 is So, in K 2 K 1 is involved, in K 3 both K 1 and K 2. Okay. So, for you one can proceed further and try to get, but we do not want to do that, because we fix finite number of intermediate points and then take the slopes and then try to do it. Okay. So, now an immediate concern is, anybody would ask, I mean, who will decide these intermediate points, who will decide these weights, and who will tell me how many points to be considered and all this stuff, right. So, we have to really consider this, and since already I mentioned this is a bit laborious, maybe somebody would start with the less number of intermediate points, so that your weighted average is done with a less number of slopes, and then you expect a little simpler method first and then slightly complicated. Okay. So, let us try to fix the number of intermediate points. Okay. Right. So, if one uses L slopes, okay, we generate K I of the form x n plus A I h y n plus h, we have taken common, then we get this kind of pattern, where I is, so it's one can identify easily, see this K 2 is x n plus A 2 h, h is common. So, A 2 K 1, K 3 is x n plus A 3 h, then h comes out, then A 3 1 K 1 plus A 3 2 K 2. So, the generalization is A 4 1 K 1, A 4 2 K 2, A 4 3 K 3, like that for K 4. So, this is the generalization. Okay. Right. So, this gets reduced to simpler forms depending on the number of slopes. So, as I mentioned, let us start with just two slopes. So, if you consider two slopes, right, then step 1 you define the method. So, we are defining the method y n plus 1 is y n plus just two slopes. So, what will we get? H W 1 K 1 plus W 2 K 2. I mean, instead of the arbitrary coefficients earlier notation, we can just generalize it. Okay. So, this is these are the weights, standard weights I have used. Now, K 1 K 2 contain arbitrary coefficients. So, what are they? K 1 is f of, and K 2 is f of x n plus A 2 h, y n plus h A 2 1 K 1. Okay. So, now what at this stage what is left? Yes, we have to determine the arbitrary coefficients and the weights. Okay. So, to do that, I would like to switch to some other notation just for convenience. because using such indices will be little nasty in the derivation. X n plus say alpha h, y n plus beta h k 1. Okay. So, I hope you follow, right. So, I am not going with these notations, just for convenience, eta 1 is replaced by beta. Okay. Now, what is the next task? So, step 1 we have defined this, that means this is going to be our method. This is going to be our RK method with two slopes, provided one determines what are the arbitrary coefficients left. The arbitrary coefficients are W 1, W 2, alpha, beta. So, these are the arbitrary coefficients. Okay. So, now one has to determine, right. So, what is step 2? Step 2 is in order to determine the arbitrary constants or coefficients W 1, W 2, alpha, beta. What we do? Already I mentioned, see what is this? This is an approximation. This is an approximate solution for the given initial value problem. So, now approximating what? Approximating the true solution. So, therefore, who is the fellow with whom we have to compare? We have to compare this fellow with the exact solution, but then exact solution is not known to us. So, what we do is your exact solution is, if it exists, I mean under the assumption of existence and uniqueness, your exact solution will be expanded in terms of Taylor series. Okay. So, now once you expand your Taylor series, compare your Taylor series with your approximation here. Okay. So, let us do that. So, in order to determine the arbitrary constants W 1, W 2, alpha, beta, expand y n plus 1, that is the approximation, in powers of h, okay, such that it agrees with Taylor series expansion of true, that is this. Okay. And how do you compare? How long? To a specified number of terms. Okay. So, now when you say specified number of terms, maybe this specified number of terms, this may define what? May define order of the so this may define order of the method. Okay. So, comparing up to this order, that means that will dictate the order of the method. Okay. So, let us do that. So, as I mentioned, it is going to be very technical. So, we have to follow the steps. So, let us expand Taylor series first. So, I am writing the TS, that is Taylor series expansion first. Y of x n plus 1 is y of x n plus so on, and we have these terms y dash is f of x and y n, y double is dou f dou x plus f x y dou f dou y evaluated at x and y n. Okay. Oh, I mean, it is better to compute the next term as well before we proceed with the comparison. So, let us it is slightly complicated, but then we need this term y 3. Okay. So, y 3 one can do it 2 f of course, all this evaluated at. So, this is, so as I mentioned, this is a slightly complicated. Okay. So, we have T s, this is supposed to be the exact. Okay. So, this is for the exact. Now, we have the approximation, this is the approximation. So, what is our aim? Our aim is to expand this in powers of h, so that we compare with this. Okay. So, it is slightly complicated. So, let us try to do that. So, now our immediate concern is to expand this in powers of h. That means, see for example, k 1 there is nothing to expand, but when you take k 2, yeah, there is, you have to expand this, right. So, let us do that. So, y 3 is done. So, now we proceed to expansion of y n plus 1. Okay. So, this I call h x p. Okay. So, k 1 there is nothing, k 2 it is better to write the form of k 2. Okay. F of x n plus alpha x alpha h y n plus beta h k 1. Okay. So, this is f of x n y n. So, it is a 2 variable expansion Taylor series. So, we have to expand this plus alpha h with respect to this variable. So, I am not writing the evaluation point. So, it is understood. At each step I have to write, but one can use a generalized notation just. Okay. Plus, now first order terms I am writing first f expanded with respect to this, then the first order term. Now, I will expand with respect to the first order term with respect to this. So, that will be beta h k 1 dou f by dou y, because with respect to this variable. So, these are first order terms plus second order terms. This is the increment. So, alpha square h square second order derivative plus the mixed term 2 alpha h beta h. So, that will be 2 alpha beta h square k 1, this is the mixed term, plus second order term of with respect to y beta square h square k 1 square plus. Well, look at this. So, we have to expand with respect to x and y. So, this is a function about the point x and y n, then first order terms alpha x dou f by dou x plus this is increment for y, therefore, the increment times dou f by dou y. Now, the second order terms 1 over 2 factorial. So, this is a second order term of this is second order term of this, and this is the mixed term. Okay. So, now this can be simplified, okay, as follows. So, K 2 is given by plus h so beta. So, we have a k 1 there. So, that k 1 is nothing but f. So, that becomes an f there plus, because what is our aim? Our aim is to compare with the Taylor series expansion. So, our Taylor series expansion has exactly this kind of form h square by 2 factorial etcetera. So, we are trying to put it in that form. Okay. Okay. So, this is K 2. So, what did we do? We are trying to get the h expansion of that approximation. So, K 1 is this, K 2 we have expanded. Now, what we have to do? We have to substitute the expansions in y n plus 1. Okay. So, let us try to do that. Okay. So, therefore, your y n plus 1 is y n plus h w 1 k 1 plus h. So, this is our approximation. So, this is given by y n plus h w 1 k 1 is just f plus h w 2 k 2. This entire expression we have to write it down, f plus h so this is the first term. Then let me put it here, Okay. So, this can be further simplified as follows. Y n plus h okay. Let me explain how we get this. Look, see, our aim is to put it in a Taylor series form. So, coefficient of h square, etcetera. So, look at this, you have one term here and with h W2 you have one f. So, if you take common, we get exactly this term. Okay. So, similarly, we get so this is the next term. So, h square, how do we get it? Look, h square W2 times this. Okay. So, now h cube will come from this term. Okay. So, plus okay, plus 2 alpha beta, it's a mixed term. So, this is our h expansion, and what was our t expansion? So, this is Taylor series expansion. Okay. This is our Taylor series with these two terms. Okay. So, maybe it is better to write down y of is y of x n plus h f plus h square by 2 dou f by dou x plus f dou f by dou y. Okay. Plus h cube by 6, h cube by 6 Okay. So, this is our Taylor series expansion. Okay. So, now what is our aim? Aim is to compare, as I mentioned, the next task is to compare the Taylor series expansion and the H expansion up to desired terms. Okay. So, that means you have coefficients of h, coefficient of h squared, etcetera. So, we compare. Okay. So, that we get some, we expect a system of equations. Let us see. Okay. So, again I would like to, this is an approximation which we have expanded in powers of h, and this is our Taylor series expansion. Now, we try to compare. So, what we do is compare h expansion and t expansion to match the coefficients of equal powers of h. Okay. So, let us look at it. So, y n must be approximating y of x n, then look, you have h f. So, h f. So, w 1 plus w 2 must be 1, because see I can so this is approximating this. Okay. Then this you have h f in this term and you have h f in this term. So, if you try to compare these two, what happen? W 1 plus W 2 must be 1, okay, right. So, let us try to do that. Okay. So, if we do that, we get from first case. Okay. Then, so let me use again red. So, this is red, these two, then the green. Now, h square. Okay. Upper I am using. Look, so you have h square by 2. So, there is a half sitting for dou f by dou x. If you remove h square, there is just a factor of half sitting for dou f by dou x, whereas here you have alpha w 2 sitting. So, therefore, alpha w 2 must be half there, and here beta w 2 is sitting for f dou f by dou y, and there is another half sitting for f dou f by dou y. Therefore, beta w 2 must be half there. Okay. So, we get this is one equation, then alpha w 2 is half, beta w 2 is half. Okay. So, this I have done it only up to how many terms? Up to order of h square. I have compared. So, y n is approximately y of x n, and by comparing this we get w 1 plus w 2 is 1, and comparing these h square terms we get alpha w 2 is half, beta w 2 is half. Okay. So, I am not comparing these three. Okay. So, that means I have compared up to terms up to h square. Okay. Right. So, now from this system, if you stop, then we should be able to determine the coefficients, but suppose let us stop at this stage, that means you have compared up to h square, then you should be able to solve, but how many unknowns you have? W 1, W 2, alpha and beta, and you have only 3 unknowns, right. So, that means you have to choose one of them arbitrary, right. So, let us say choosing alpha non-zero, okay, we get beta equals to alpha, W 2 is 1 over 2 alpha, W 1 is 1 minus 1 over 2 alpha. Okay. So, with this our approximation becomes y n plus h. What was our approximation? This was our approximation, h into w 1 k 1 plus w 2 k 2. Okay. So, we have w 1. So, h into our w 1 is 1 minus 1 over 2 alpha k 1 plus w 2 1 over 2 alpha. So, this is our approximation where k 1 is given by f of x n plus alpha h y n plus alpha h k 1. So, this is our Arke method. Still alpha is arbitrary, right. Still alpha is arbitrary. So, now you can talk about specific values. Okay. So, let me write this as R k 2, okay, because I have compared only up to h square. So, therefore, maybe we are optimistic just by comparing up to h square, we can call this method second order probably, right. Anyway, we can discuss that. So, now since alpha is arbitrary, let us take some specific value and try to see. Okay. Right. If alpha is half, then beta is also half, then what will happen to your method? Alpha is half, right. So, this fellow is 0 and this fellow is 1, right. If alpha is half, this fellow is right. Okay. So, let us if alpha is half, beta is half, then we get W 1 is 0, W 2 is 1, and your method reduces to y n plus 1 is y n plus W 2 is 1. So, h f of x n plus h by 2 y n plus h by 2 f. Okay. So, this is the method we get. Okay. So, y n plus this is the method, alpha is half. So, this coefficient vanishes and alpha is half. So, this is so we get W 1 0, W 2 is 1 and beta equal to alpha equal to half. Okay. So, therefore, the method reduces to this one. Okay. Suppose alpha equals to 1, then beta equals to 1, then W 1 equals to half and which is also W 2. Okay. So, in this case y n plus 1 y n plus, so h times W 1 plus W 1 k 1 plus W 2 k 2. So, this reduces to h times k 1 plus k 2, and what is our k 1? K 1 is f and k 2 is f of x n plus alpha h y n plus beta h k 1. This reduces to f of x n plus h y n plus h k 1, k 1 is f. So, this is the particular case when alpha is 1 alpha. So, these are general choices. Okay. So, now the story is not left. We have compared up to 2 terms and then shown a system of this form, and then one is arbitrary. So, of course, taking non-zero, one can have different choice, right. So, the general choices are alpha is half and alpha is 1, right. Now, what happens to the terms beyond h square? Yeah, obviously, they should contribute to the error. So, if you consider the difference, okay, since T expansion and H expansion agree up to h square, okay, what will happen to the difference? So, the difference must be the residual, that is error. So, naturally that should start from h cube. Okay. So, if we can do the long calculation, y 3 we have computed, anyway this is in our hand. Okay, plus so this is the residual which is supposed to be the error, of course, at a given, okay. Since we know f and we have determined alpha, okay. So, what will happen? This entire thing is known to us and hence this is order of h cube. So, the residual is of order h cube, okay, and hence the method is of order h square. Okay. So, one remark, see for example, here for all f means not for a particular f this is becoming 0 and all that. For all f, no choice of alpha will make the leading term vanish. What is the leading term in this? This is the leading term. Okay. So, further you have h 4 etcetera etcetera. Okay. So, no choice of alpha make the leading term vanish for all f of x y. Okay. So, this is an important remark to conclude that really the error is coming from order of h cube. Okay. So, we have approximated with two slopes and generalized formula, but we have considered only two slopes and then we have taken the weighted average and expanded the approximate formula, expanded the Taylor series formula and then determined the arbitrary coefficients by comparing both of them up to h square, right, and then conclude that the residual comes from h cube and hence this is a second order method. So, this is hence it is RK 2, that is what I have written. It is a, so now suppose one would like to define a higher order method, higher order RK method. What one has to do? One has to compare the terms between the Taylor series expansion and the H series expansion of the approximate and try to determine the arbitrary coefficients. Okay. So, this will determine the method, because once you determine the coefficients, the method is determined and then you get a new method. Okay. So, how long we try to determine? Of course, this is algebraically, if you try to do it, you get very complex system. So, the standard methods are, first when you arrive at a second order method, there is a choice of one arbitrary coefficient, and more general choice are half and 1, right. So, these are RK second order, but they slightly vary. Now, if you really go for more number of terms, then you get, let us say you go to 4 terms, then you get 4 in the sense you go to compare up to h power 4, you get fourth order RK method, right. So, that will be slightly complicated. So, before we go for that, let us just see some example. Okay. So, this is y dash is x square plus 2 x y and y of 0 is 1 and say h is 0.1. Okay. So, then whatever the method we have determined, let us say alpha 1 case. So, alpha 1 case we have y n plus 1 is y n plus h by 2, k 1 is just f there, plus k 2 is f of x n plus h, y n plus h f. So, this is the method we have. So, suppose we try to determine y of 0.1. So, this will be y 0 plus f of x 0 y 0 plus f of x 0 plus 0.1 y 0 plus 0.1 into f of so we have to compute each term. So, what is f of? So, this is x 0 square. So, x 0 is 0. So, this is 0, right. Right. So, therefore, so y 0 is 1, h by 2 this is 0 and f of we need this term, right, and this is 0. So, this reduces to this is 0. So, this is gone, this reduces to f of 0.1 and 1. Okay. So, this is 0.1 square. Okay. So, this will be so where we are. So, point h by 2 this is 0 and this is reduced to okay. So, we get the value. Okay. So, next we compute. Okay. So, a good exercise for you is for the same example you try to compute the values, at least 2-3 values y 0.1, 0.2, 0.3 using Euler method and then RK method, and since the form of f is very simple, one can compare with the exact solution to know which gives slightly accurate. Okay. So, in the next class we try to talk about RK fourth order and maybe once we define the order of the method, then we have to talk slightly more about the error, and at for example, you are computing y of 0.1, right, then there is some error introduced at that stage. Then to compute y of 0.2 you are using the value of y of 0.1. So, whatever error introduced at 0.1 that will propagate, right. So, we have to really think of how these errors will be propagating and try to control. Okay. So, we will talk on RK fourth order etcetera, and then how in general error estimates are computed etcetera. Thank you.